Eicosanoids play a key role in regulation of vasodilation, vasoconstriction, and or platelet aggregation. And so as such, eicosanoids can really be very important in terms of vascular health, regulating vascular health. So we will talk about two important eicosanoids that are produced by two different cell types. Prostacyclin PGI2 is produced by endothelial cells. Thromboxane A2 is produced by platelets. Both play a key role in the maintenance of vascular health. Importantly, both are produced from a common pathway, which is the cyclooxygenase pathway, by a common enzyme, okay, by COX-1 and or COX-2. So, thromboxanes are produced by platelets. Their main effects is to promote vasoconstriction and platelet aggregation. On the other hand, prostacyclin PGI2 produced by the endothelium, promoting vasodilation and inhibiting platelet aggregation. So in many ways, there's a tug of war between thromboxane A2 and PGI2, meaning their relative amounts will determine what state the vasculature is in and what state the platelet aggregation is in. So if you have higher amounts of PGI2 relative to thromboxane A2, you will promote vasodilation and you will inhibit platelet aggregation. And the reverse would be true. Higher thromboxane A2 would promote vasoconstriction and platelet aggregation. So many of you might be familiar with the use of aspirin as and at low doses to improve vascular health. And this is how aspirin will affect vascular health. Aspirin will acetylate cyclooxygenases, both isozymes, COX-1 and COX-2. Only COX-1 is shown here, but basically it will have the same effect on both COX enzymes, COX-1 and COX-2, and in doing so, by adding this acetyl group to the active site of cyclooxygenases, it will irreversibly inhibit the enzymes, irreversible inhibition. So that means those enzymes can no longer participate in the synthesis of any prostaglandin or eicosanoid. So here's the effect of aspirin, inhibiting irreversibly cyclooxygenases. In platelets, the outcome of that inhibition is a reduction in thromboxane A2. On the other hand, in endothelial cells, cyclooxygenase is inhibited by aspirin as well. However, the outcome of that is no significant effect on the amount of prostacyclin produced by endothelial cells. So the net effect is that you reduce thromboxane, you keep PGI2 about the same, you have higher amounts of PGI2 relative to thromboxane, you are going to promote vasodilation and inhibit platelet aggregation, and that's the desired outcome of the slow aspirin therapy. So you decrease platelet aggregation because of the reduction in thromboxane A2. Prostacyclin synthesis in endothelial cells remains about the same, and therefore you promote vasodilation and inhibition of platelet aggregation. So how does this work really? Importantly, before I explain exactly how it works, I want to remind you that aspirin will inhibit both COX-1 and COX-2 irreversibly. Now, in platelets. Once that COX-1 enzyme is inhibited, because platelets are anuclear, that means they aren't able to synthesize new enzyme, produce new enzyme. The enzyme that is present in the platelets is irreversibly inhibited, and therefore the synthesis of thromboxane in platelet will be decreased. The enzymes that are present in endothelial cells will also be inhibited by aspirin. However, endothelial cells are nucleated and they can recover by producing more COX-1 and COX-2, meaning more enzyme is expressed because they are nuclear. And the newly expressed enzyme that has not been exposed to aspirin can essentially continue to make prostacyclin, so the normal amounts of prostacyclin are produced by endothelial cells. Hence, the balance favors prostacyclin over thromboxane, and that's the net effect of low-dose aspirin on promoting vascular health. And just a quick reminder here, again, on another summary, really a reminder is that we talked about aspirin here inhibiting both COX-1, COX-2. All NSAIDs will also inhibit COX-1 and COX-2. Importantly, aspirin is the only irreversible inhibitor of COX-1 and COX-2. Second reminder is corticosteroids can inhibit the upregulation of or induction of COX-2 due to some stimulus like tumor promoters or endotoxin. And thirdly, cortisol or corticosteroids can inhibit the production of arachidonic acid by inhibiting phospholipase A2. So cortisol has two sites of action, inhibition of phospholipase A2, and in doing so it can affect the synthesis of all eicosanoids. That means leukotrienes, prostaglandins, and thromboxanes. Okay, so we talked about a couple of important, the presence of other pufas that can be used to synthesize eicosanoids. We have primarily been focused on the eicosanoids derived from arachidonic acid. Arachidonic acid is derived from linoleic acid, which contains two unsaturated bonds or double bonds, and that's the designation 2. So all the eicosanoids that are derived from arachidonic acid will be given the designation 2. So PGI2, thromboxane A2 come from arachidonic acid, and we've already discussed their effects. There's another group of minor eicosanoids that are derived from linolenic acid. Linolenic has 3 double bonds. It is another family of essential fatty acids, and this is the omega-3 family. Again, the 3 here represents the 3 double bonds in linoleic acid. Linoleic acid, when metabolized, can produce eicosapentaenoic acid, which is a 20 carbon molecule with 5 double bonds. It can be used as a precursor to produce corresponding prostaglandins and thromboxanes, and they are therefore given the designation PGI3 here and thromboxane A3. So this is just a quick reminder. You don't need to know the details here, but linoleic acid can be desaturated. This is what we get from the diet. This is again the omega-3. Remember, this is the methyl end. That's why it's called omega-3, because we're at the position of the double bond. and again you have desaturation, elongation, desaturation, you form this 20 carbon molecule with 5 double bonds. And this molecule can replace the arachidonic acid present in membrane phospholipids. Okay, so this is what you want to think about if you have a diet that's high in a linoleic acid. So if you have a lot of EPA, it will replace arachidonic acid in the phospholipid membranes, and when phospholipase A2 is activated, it will release EPA instead of arachidonic acid. So then this EPA, which is from the 3 series, will be used to make eicosanoids of the 3 series. Therefore, you will get prostaglandin, prostacyclin, PGI3, and thromboxane 3, thromboxane A3. So basically, it turns out that thromboxane A3 is a lot less potent than thromboxane A2. So that will promote less platelet aggregation. PGI3 is about the same potency as PGI2, and this idea suggests that may suggest why omega-3 diets may contribute to reduced platelet aggregation and perhaps improved and vasodilation. So now we're going to talk briefly about the synthesis of leukotrienes. And leukotrienes are the third group of eicosanoids that can be derived from arachidonic acid. Again, they have this important common initial step that they share with the other eicosanoids. They need arachidonic acid to be released by phospholipase A2. Again, this is a stimulus-dependent process going through a G protein coupled receptor. Once arachidonic acid is produced, it's going to be metabolized by a new enzyme or a different enzyme, 5-lipoxygenase, LOX. That produces an intermediate called hydroperoxyeicosatetraenoic acid, HPET, which then is converted to LTA4 if you want the parent leukotriene. So LTA4 is an important parent leukotriene that is used to make the other leukotrienes from LTC4 to LTF4. Importantly, these leukotrienes from LTC to LTF are the bioactive leukotrienes, meaning they are the leukotrienes that will have cellular effects. Second important thing I would like to say about leukotrienes is that leukotrienes typically, these guys down here, are involved in hypersensitivity reactions and allergic reactions, unlike prostaglandins and thromboxanes, which are more strictly involved in inflammatory responses. So just quickly here again, LTA is the intermediate, LTB4, and here's all the cystenyl leukotrienes. These leukotrienes are made by the addition first of glutathione, and then you can remove parts of this tripeptide to form LTE4, LTEF. Anyway, all of these from LTC4 down are the bioactive leukotrienes, and they are referred to as the cystenyl leukotrienes. So one important reminder is that cortisol will still have a very important effect here on phospholipase A2. Again, by inhibiting phospholipase A2, you won't produce arachidonic acid. You will not synthesize any leukotrienes as a result. So cortisol can be used again to suppress the synthesis of all eicosanoids. One important thing is that you don't need to know the exact details here about the synthesis of these leukotrienes. Just know that these are all referred to as cystenyl leukotrienes, LTC through LTF4. Finally, it's good. These leukotrienes that are bioactive are an important component of what is called the slow reacting substances of anaphylaxis. Most of these cystenyl leukotrienes are produced during anaphylaxis and other allergic hypersensitivity responses, and then they're going to have various effects on vascular permeability, bronchoconstriction, and vasoconstriction. One such example of the effects of leukotrienes is asthma. Asthma is an allergic response associated with airflow obstruction, increase in secretion of mucus, bronchoconstriction, and infiltration of inflammatory cells of the airway walls. So most of these effects are really due to cystenyl leukotriene production. So treatment of asthma, for example, can involve one of three strategies. You can get a receptor antagonist, leukotriene receptor antagonist, that prevent the effects of leukotriene on their respective receptor. You can have a lipoxygenase inhibitor, meaning you inhibit the synthesis of leukotrienes in cells, so that's another strategy. The third one, which is more the comprehensive strategy, meaning is the use of corticosteroids, which inhibits the release of arachidonic acid, and that will inhibit the synthesis of leukotrienes as well as prostaglandins and thromboxanes. And this is really a good summary table for some of the things to recall about this eicosanoid lectures. Is initially everything starts with the activation of phospholipase A2 producing arachidonic acid. There is one pathway that is responsible for the production of prostaglandins and thromboxanes, and that's the cyclooxygenase pathway. Okay, involves either COX-1 or COX-2. The other pathway involves the lipoxygenase pathway, which is responsible for the production of leukotrienes. There are several important sites where you can inhibit or affect inflammation. NSAIDs are very important regulators of inhibitors of COX-1 and COX-2, aspirin being the most important irreversible one. You don't need to memorize names of the NSAIDs, just know what their site of action is. They will affect primarily the synthesis of prostaglandins and thromboxanes. No effects on leukotrienes. Corticosteroids can inhibit phospholipase C, prevent the release of arachidonic acid, and the release of arachidonic. Without arachidonic acid, none of the eicosanoids can be made. Okay, so corticosteroids is a very potent anti-inflammatory agent because of its inhibition of phospholipase A2. Corticosteroid can also inhibit the induction of COX-2, which is the second isozyme of that is inducible.